Thank you, Ameya. So welcome. Once again, I'd like to welcome each one of you to the PI seminar series dedicated towards advancements in scientific machine learning. And today I'm pleased to invite as well as welcome Dr. Romit Malik, who is joining us from Penn State. Dr. Romit is an assistant professor in the College of Information Sciences and Technology at Penn State. He's also a co-hire in the Institute of Computational and Data Sciences at Penn State and a joint appointment faculty at Argonne National Labs. He obtained his PhD in mechanical and aerospace engineering at Oklahoma State University and was the Margaret Butler postdoctoral fellow before becoming an assistant computational scientist at Argonne National Labs. His group mainly works on high-performance scientific machine learning algorithms and its development with applications specific to multi-physics nonlinear dynamical systems, such as fluid dynamics, weather, and climate modeling. Nuclear fission and even beyond applications beyond that. And he's also an early career awardee from the US Army Research Office. And today he will be giving us a talk mainly on his research on neural ordinary partial differential equations for scientific machine learning. Maybe a quick brief overview of what he's going to be, what the talk is going to be. Maybe I can also give you that. So basically, he'll be mostly dealing with neural architectures and algorithms in neural ODE paradigm that leverage partial knowledge of the underlying dynamics to obtain surrogate models that can recover the correct chaotic dynamics for a wide range of applications, such as turbulent Navier-Stokes equations or planetary atmosphere and ocean systems. So without wasting more time, I'd like to hand over the platform to Dr. Romit for the rest of the session. Thank you.
Okay, thanks, Siddharth, for the introduction, and thank you all for coming to this talk. I'll try to cover as much as I can today, but if there are any questions or if anybody wants to schedule a chat after to go into some of the details, more than happy to talk to you later. So let me share my screen real quick and we can get started. So, okay, where is the slideshow? Okay. I'm assuming you guys can see my screen, right? So.
Yes, Romit, it's visible.
Okay, great. So yeah, thanks again for the introduction and for, of course, the invitation to speak. Really delighted to be here. I can start with a slide that kind of sums up what Siddharth was saying, but something that if people are doing machine learning will resonate with. The motivation that brings me here today, and the research I talk about today is motivated by chaotic dynamical systems, and we interact with many such systems, such as the weather and the climate, and also in various engineering applications. And some of the properties of these systems are that they are dynamical, of course, but they also have certain invariant properties. So if anybody's ever simulated the Lorentz system of equations, you know that in this system of ODEs, no matter where your initial condition is, where in this three-dimensional universe your initial condition is, you end up following you end up falling back onto an attractor because the system is a dissipative system, right? So this is in some sense a system that is sensitive to initial conditions, but has an invariant property that is insensitive to initial conditions. The fact that a system eventually rests on this attractor and then stays on it forever, right? Now, this is in stark contrast or as opposed to how typically people learn dynamical systems using machine learning, which is usually through the use of some sort of metric minimization, such as the mean squared error. In chaotic dynamical systems, such as the weather or even these toy problems, minimizing mean squared error is essentially a no-go because that can give you short-term accuracy, but in the long run, there isn't a metric that you can actually calculate a loss against and then find a gradient of to inform a model to behave in the appropriate manner. So this is the motivation, right? So what do you do when mean squared error doesn't work? And so this is kind of what is summarized over here. If you think about short-term forecasting of systems that you have minimized with mean squared error type of behavior, you can, for example, I have an example of a sea surface temperature forecasting. We'll get back to this at the end. But a standard, transformer, RNN, LSTM, doesn't matter. Any type of method you pick up, you can get a short-term performance that again is based on your mean squared error being low during training, but in the long run, you don't get the right behavior, right? Over here, there is an invariant type of behavior, which is actually the climate, that you don't get, even though you do get the weather, right? And so the question then becomes, how do you learn something about this system and specifically the physics of the system when you cannot optimize for it, right? And in our group, and in this talk in particular, we try to develop these novel algorithms so that we can discover these invariant statistics, even though we have short-term data, right? We do this using a variety of methods. One method is to impose structure, right, to build in some inductive biases into an algorithms that can do this. The other method is to change the optimization task itself, and I'll go through both of these today. So a little bit of a background information. I come from the world of numerical methods, just like Ameya. So we are very comfortable with solving systems of equations numerically. And so the starting point for the work today is from a machine learning technique that is in some sense within our comfort zone, which is learning the right-hand side of a system of ODEs, right? So if you think about a system of ODEs that are given as such, the du by dt equals the right-hand side, which is a function of u. We are very familiar with using different numerical methods to solve this. The inverse problem, which is frequently looked at in machine learning, is how do you use snapshots of the evolution of the system? These don't have to be equally spaced, but assume equally spaced for now. How do you use these to back out what the right-hand side is? And when I say back out, you can parameterize the right-hand side as a neural network, but there are other approaches where you can parameterize this as polynomials or dictionary type of approach as well, right? And so we still haven't solved the problem I introduced because I'm still using a mean squared error, but this is a starting point, right? And that this is called a neural ODE. The approach to optimize the neural ODE, as I mentioned over here with F, there are different approaches. The first approach is to write the discrete representation of this into a automatically differentiable capable framework such as PyTorch and TensorFlow and just optimize like you would a neural network. The other approach is to write down the adjoint of that particular system and then use the adjoint to compute gradients with respect to some quantity of interest. In this case, again, a mean squared error loss, right? The adjoint gives you memory efficiency versus a standard implementation of the discretized differential equation in a sort of a neural network package gives you memory inefficiency, but it's also easier to use, right? Okay, so but that's a little bit of a background. We're not going to talk that much about how to train these things in the short term. We'll get back to this a little later. So some of the things that we have been looking at to actually solve this problem have been based on the understanding that as modelers of dynamical systems, we typically can introduce templates into the right-hand side of the neural ODE. So for example, if I know that my system is a chaotic system that has a dissipative behavior, which means that, again, that no matter where my system starts in phase space, I sort of fall onto some sort of manifold, then you can try to build certain characteristics of this system into your neural ODE. So for example, in this paper over here, I introduced a approach to basically parameterize the right-hand side of the system, not merely as a black box, which I show over here. This is just the same as the expression I introduced previously with the right-hand side that's a neural network, but split the right-hand side into a combination of a linear term and a nonlinear term. And specifically, the linear term was designed in such a way that you could basically guarantee the existence of dissipative behavior, right? So the linear term, for example, we could assume that it's banded and symmetric, just like a finite difference stencil for your finite difference solve of this equation. And then you could just learn the coefficients of this scheme. So it's like learning the central difference scheme, for example. And the reason we went down this route is because if you look at a lot of chaotic dynamical systems, you do have linear terms in there that give rise to so-called invariant manifolds. And we could discover these invariant manifolds by prescribing this form and then learning, right? again, the loss remains the same. It's still a mean squared error, but there's structure in the right-hand side of my neural ODE that helps me to discover the invariant manifold. In terms of how this actually looks like when we deploy it, I have a prediction for what I call what is called the KS equations, the Kuramoto-Sivashinsky equations. It's a 1D PD that is again discretized, in a periodic sense over a domain and evolved in time. I have two columns over here. The first column shows how this system may evolve in the short term, and the second column shows after you evolve it for a really long duration in the future. All these methods are trained, rows 2, 3, and 4 are trained using a mean squared error, so that hasn't changed. The first row is the ground truth, is the data. Again, we train this by sampling conditions on the attractor, and we roll out for a short duration, right? Because again, if for a long duration, mean squared error doesn't make sense. So if you were to fit just a regular neural ODE, what is a regular neural ODE? Well, with the right-hand side is a black box, right? We just fit the right-hand side. Then again, in the short term, we actually get something that looks physical, but as we integrate this out into the future, you lose the physics of the system. If at all, you remain stable. You might have nans creep in and then basically blow up your code. You could, of course, this third row over here is what I call the row where we cheat, where what we do is we know how the linear term looks like for the KS equations, which it looks like basically this second order term and this fourth order term. I can discretize this myself again using a finite difference stencil. And I can impose this discretization into the linear term over here, which then leads me to, as you can see, short-term accuracy as expected. But in the long run, of course, these fields have no business matching because it's a chaotic system, but I stay stable. I have more quantitative assessments in a bit. And this fourth row is one where I not only do I impose that linear term, but I actually learn what the discretization is. So it's in some sense, I'm trying to learn from the optimization what these linear terms are in a separated manner, and as a result of that, I still get both short-term physicality and long-term physicality. If you were to actually do a quantitative assessment of this behavior, what I plot on the left is ensemble average metrics for the error, the root mean squared error between the mean squared error between the ground truth and the predictions of an ensemble. And as you can see, they're all about the same. I wouldn't call one better than the other. And you see the hallmark of deterministic chaos, like the error grows initially, and then basically it's supposed to saturate over here because the systems basically are in completely different areas of phase space. But what is more interesting is if you actually compute the invariant statistics of the KS equations, which are very interesting. You can plot, for example, 2D probability density function of the first derivative of the state and the second derivative of the state, and this gives rise to this teardrop shaped or pear shaped density function. Over here, you can see, even if my neural ODE is stable and stays bounded in the long run, which we saw over here, it's obviously obvious to the naked eye that this is not right, but it shows up in that invariant statistic. You don't get the right density. Whereas if you impose the linear and nonlinear separability and then structure, you can recover this attractor when you exactly specify the linear term. This makes sense because you've cheated in some sense, or when you learn it out of these systems. So this is something that is quite useful. So this metric, unfortunately, is not something I can optimize against, right? So I have to hope that my learning and my architecture actually extract this metric given short-term data from which this metric cannot be built, right? So that's kind of a summary of the problem that we'll be dealing with throughout this talk. Okay, so the advantage, and this is just a sidebar over here, but the advantage of having this linear-nonlinear separability is that the nonlinear term admits an eigendecomposition from which you can back out a spectral gap. So this A term was learned from my optimization, so I can do an eigendecomposition of the A term. I can keep a subset of the eigenvectors, which lets me identify a projection matrix, like a spectral decomposition. This projection matrix can be used to reduce the dimensionality of my neural ODE. So you can think of this as what I call flipping the script. So usually when people are learning dynamical systems, The idea is that you want to reduce the dimensionality of your high dimensional system and then learn a system in the latent space. But here you can learn a system in the original space and then discover what the intrinsic coordinates are using the linear term that you have actually extracted, right? And in the approximate inertial manifold theory, you can assume that there's a spectral gap that exists. So some coordinates actually show non-stationarity versus the other. So you can only keep those coordinates, and then the rest of the coordinates can be basically ignored. So you can set dq by dt equal to 0, and then get a relationship for q as a function of p, and this can be plugged back into an equation for p alone, which gives you a reduced system, right? So that's an advantage of actually leveraging structure. What I show over here in this plot is that by actually reducing the dimensionality of your system, you of course introduce an error as you go from right to left. But what you have effectively over here is that the blue circles are when I correct for my non-stationarity coordinates, non-stationary coordinates. My crosses over here are when I do something called post-processing. So after I extract my P's as if I did not have Q's, I model the effect of the Q. And the orange line is if I ignore Q altogether, if I set Q equal to 0, right? And so what I'm showing over here is that that after an intrinsic dimensionality, basically I fully resolved everything over here. This roughly corresponds to 16. So after 16 eigenvectors being resolved, it doesn't matter anymore. You have captured the invariant statistic very well. So the y-axis is the KL divergence. So it's basically, you can think of this as a distance between the ground truth and the prediction in the density space. Okay. So this is like a reduced order neural ODE that you can learn from your high order data, right? So that's nice. Complicating this slightly is this idea of the differentiable physics approach. What motivates this particular portion of my talk is the fact that, you know, frequently, usually over the last, as a result of the last century, we have a whole host of solvers that exist that can efficiently implement numerical methods, for example, for the linear term that I mentioned. So if you set up a problem where you learn a correction to a system of equations given by a neural network, you can interpret this as a neural ODE training, where now instead of having a linear term that is coming from a simple finite difference scheme, you could have a linear term that is coming from a very complicated solver, right? And your goal is to learn a correction to that solver, so almost like a closure model, if you're familiar with turbulence. And that is what we use as a motivation over here. So over here, what we have is a finite volume. It can be anything really, a finite volume, a finite element, or finite difference solver that implements a system of equations, a PDE. And this PD may have linearities and nonlinearities, and your idea is to correct the system of equations given some sort of ground truth data, right? And so what we do over here, for example, is we have again, we're still not quite fully solved the problem of chaotic dynamical systems, but I'm building the machinery towards that. Let's say we have sparse data from a flow field that is coming from some experiment or from some other source of information, and I have a solver that is not perfectly aligned with that information. So I want to minimize the error between the ground truth, which is the state, and the prediction from my solver. Then I can build a correction into my solver, and then backpropagate through the combination of things. So differentiate through a numerical solver to learn a correction. So for example, let's say I look at a problem of turbulent Navier-Stokes, which is two-dimensional, which is, again, some people claim this is not real turbulence. I completely agree, but this is a prototypical problem. And if I have insufficient resolution, I can solve the Navier-Stokes system in the vorticity stream function formulation, but I will need to model a correction term in the vorticity equation to account for insufficient resolution of all the frequencies in my flow field, right? And so the approach over here is, again, very similar to what we've been discussing so far. You have a system that evolves in time, and our goal is to match the trajectory of the evolution. but we want to build in some inductive biases into our machine learning model so that we have some desirable property in the sense of some quantity of interest, right? So over here, the experiment we conducted was to match the evolution of a direct numerical simulation, so the evolution of a fine grid simulation of this very same problem, but have the statistics match on the coarse grid, which is subsampled by a factor of 4 in each dimension, so 16 overall. In this particular application, since we have a vast majority of the dynamics already built in as a result of actually having a solver, right? The solver has the quadratic nonlinearity, it has the linearity, it has all the Poisson solve, everything built into it. Our goal was to correct just the error due to the nonlinearity by introducing a subgrid stress term, which is typically used in turbulence closure. And the subgrid stress term was modeled as a linear dissipation as well as a nonlinear correction. And these are details which I can point you to in our paper, but we tested a whole bunch of inductive biases to model this nonlinear correction. Usually this comes from integrity basis of tensors. But this idea of having a neural ODE train a correction to known physics is quite nice, because what you can see is that if I then compare the true evolution of the system versus the corrected evolution of the system as a result of this machine learning correction, you can see the flow fields are correlated for a long amount of time, as against, of course, not using a correlation, because when I say subsampled, I mean that my resolution has been reduced to an unacceptable amount, which causes my dynamics to essentially not be resolved and then blow up effectively. And of course this is for a testing configuration, so my Reynolds number is different from my training configuration, but I still stay stable. And so this is an example of how you can essentially build in knowledge about your system of equations into your neural ordinary differential equation to engender some sort of desirable outcome. And I think I've accidentally unhid a slide that has an important schematic, so I will show this very quickly. The advantage of having this this approach where a vast portion of the physics is pre-specified through a solver or through your intuition, because you know about the system, leads to much better generalization and much better stability in the long run. So over here on the left, I show you the angular average kinetic energy spectra. So this is similar to a metric that I mentioned in the KS equations, which should stay well behaved in the long run. For example, if you have a forced turbulence case, and what I show over here is predictions for different cases. So this is kind of a case where the turbulence decays over time. This is what we trained on. This is where turbulence is forced, so it never decays. And so your invariant statistic is actually the spectrum. The spectrum never dies. The energy always stays. Then you have force, but at different Reynolds numbers, which are challenging generalization cases. And as you can see over here, that the predictions from our physics our model with the physics embedded in it typically performs well in recovering this invariant statistic, even though in the short term the correlation drops to 0. This is again a chaotic system, so short term you get some sort of adherence to the right structures, but in the long run, what we really care about is a metric like this, where we recover the right scale separation or the right multiscale behavior that we expect from this type of system. Okay, so let me then go back to the right slide. I don't want to play from the start. I want to play from here. Okay. So I try to sell you on the idea that if you know about your system, you should put it into your Neural ODE or any method really, and try to kind of constrain it through hard or soft approaches. But in many applications, many critical applications, you don't really know the specific formulation of the dynamical system, right? So all you have is data, and then in such cases, you essentially can't cheat or semi-cheat by putting knowledge of the physics into your formulation. And so then I say over here, we are forced to tackle chaos head-on, the problem of chaos head-on, right? And so this is something that significantly increases the complexity of your task. But we have made some progress in solving this equation, right? So what is the main issue with learning chaotic systems, right? The main issue with learning chaotic systems is that the gradient of a chaotic system is the computation of the gradient of a chaotic system is fundamentally an ill-posed formulation. So even for something as simple as the Lorentz equations, which I repeat over here, and an objective where I'm saying that I want to compute the gradient of J with respect to a parameter in the system where the objective J is basically like an average of the state component Z. So basically, as Z changes over time, as the system traverses the three-dimensional space XYZ, I just want to record Z every time and then average it, right? And if you actually plot J as with respect to rho or one of these parameters, and let's say you do a brute force plotting, so it's a simple system, so you can integrate it several times and compute these statistics. You actually see something that to the naked eye looks like having a gradient of 1, effectively, right? To the naked eye, it doesn't look. But if you actually compute gradient of J with respect to rho using, I don't know, automatic differentiation or an adjoint, you will see that the gradient is absolutely useless, right? So you see that the gradients are exploding to very high numbers, which is it encapsulates the problem of learning chaotic dynamical systems with machine learning. The machine learning needs gradients. Chaotic dynamic systems give you horrible gradients, right? So how do we solve this problem? And so our approach to solving this problem is related to there's a citation that's missing over here, but this is from some work done by Jonathan Freund at UIUC, who explored ideas of computing gradients through turbulent simulations. The idea is if you think about gradient computation as evolving a trajectory forward in time and then computing its adjoint backward in time, then the issue is for long-term simulations the error grows, right? And also for very long-term simulations the error makes no sense. So computing an adjoint with respect to that error J causes you to have extremely high gradients which are not physical. So our approach, inspired by him, but with a slight modification, relies on chopping up this forward evolution of our machine learning model. It doesn't have to be a neural ODE, it can be anything, into these non-overlapping windows. And then at each window, we introduced what we call like a slack variable, like a learnable parameter which captures the difference in the final condition of the previous window and the initial condition of the new window. So let me repeat that. So chopping this trajectory into multiple windows is probably something that is easy to understand. But what I've introduced in addition to the trainable parameters of my machine learning model, or for example, for the Lorentz system, the 3 parameters in the Lorentz system, I also introduce another learnable parameter which says how different is the final condition of the previous window and the starting condition of the new window, right? And then our goal is to basically reduce these parameters over time, right? So if you think about what the objective function becomes now, you have the standard objective function, which is summed up mean squared errors across these individual windows. But in addition to that, we introduce what is called a weighted penalty. This penalty says that initially, the trajectories are allowed to be having different initial and final conditions, which are given by the difference between, say, T1 minus and T1 plus. And over time, the difference between them must be minimized. So so the way we do it, again, we basically compute the difference between these two endpoints, and over time we don't impose these things to be exactly on top of each other as we do in the standard unrolling of a neural ODE, but we gradually enforce it, right? And when we do that, we see something remarkable. Well, firstly, when we compute the gradients, for example, for the Lorentz system that I showed you, you can see that the gradients are much lower compared to if you just use a vanilla automatic differentiation or adjoint method. The gradients are much higher. This is for the Lorentz system. The circles that you see over here on the left are when the penalty strength changes. So the idea is that over time, my gradients are computed as the right hand side of my dynamics is updated. And frequently, as the right-hand side changes, the gradients start rising. And the reason they start rising is because of the chaotic problem that I introduced. And then the penalty strength is basically updated. It's increased to make sure that the trajectories stay close to each other when they start diverging. And so over time, this is almost like an approach that keeps the gradients flat. And when we do a decomposition of the gradients over here, so remember the gradient is now not only the mean squared error, but also this penalty. So the optimization loss and the penalty loss, as you can see, they are different, but the discontinuity loss is what we want to really drive down to zero, right? And so this as you can see, frequently the use of the penalty strength updates causes this to drop down to zero. And of course, the overall optimization loss is also driven to a lower value than, let's say, just using a regular neural ODE.
So Romit,
And
just
yes,
one question.
yes.
So are you training these say time domains parallelly or sequentially?
You can do it in parallel. Yes.
Okay. So
So yeah.
when you do it in parallel, so
Mhm.
basically you have to wait till your kind of a interface loss, like delta Q, the difference between your initial and the final state at the same location should
Yes,
reduce.
for pairs of windows, yes.
Yeah, but the way they are, they will basically converge is from say from lower time to higher time, right? Because until and unless your lower time solution has converged, the final solution will not converge, right? So even though you are
Yes.
doing this parallel.
Yes, yes, yes. You're right. Absolutely. There is a bottleneck of communication that we introduce over here. Right.
Okay. Okay.
We have some tricks to deal with it, which we are working on at the moment. We
So
use
basically, well, in that space only, we do introduce as the time domain decomposition, but
Mhm.
we use the sequential way because we know that until and unless lower time solution converges, there is no
Yes,
point on start training for the higher time. Second
correct,
thing, we
correct.
also use and in fact, you can also try the causal weights. So you have
Mhm.
large weights uh, towards the initial condition, and that actually exponentially decreases as you
Yeah,
train.
I think that's kind of similar to what we are doing over here as well. You're right.
Okay.
Yes. Yeah. Yes, but yes, what we do now to accelerate this process is we actually do gradient truncation. So when we are back propagating through a large rollout, we basically don't back propagate all the way back. We just chop off the gradient earlier. So, but yeah, but there are these interesting methods that people are using to deal with this problem of long-term rollout error. When we actually visualize the loss surface as a result of this of this kind of regularization, you can see to the naked eye that the loss surface is actually much smoother for the Lorentz system. This actually makes sense, and that's why our optimization is behaving a lot nicer. And so this is kind of a summary of what we are trying to do. Our goal is to learn a neural OD from chaotic data, and we basically have a a system where we learn the right hand side, where in addition to the mean squared error, we also have a penalty that accounts for the, as Ameya said, the discontinuity at intermediate windows. And this is just another summary of the same thing. Okay, so if you go back to the KS equations and we basically redo the analysis to now look at the shape of the attractor as a result of embedding this or focusing on the optimization as against the imposition of structure, you can see that we don't do as well as the stabilized neural ODE. The stabilized neural ODE is the approach where we explicitly specified a linear term, but we had to assume there was a linear term. We do get a better capture of this attractor shape. We extract an attractor as against the neural ODE, which may or may not extract an attractor and may blow up. But we don't get this this sort of island in the middle, or island of no density in the middle, which just tells you that you know your um, physics makes a big difference. If you can impose it, if you know it, you should always try to do it. And then in terms of training times, the convergence is faster because, again, we have effective gradients now, and so we end up getting you know, like a more performative behavior. But I also want to you know, sort of emphasize what Ameya said, that there is an off-nominal sort of communication that you have to do across windows, which can be a little more complicated on the engineering side, right? So okay, so one thing that we wanted to check as a result of this is, well, do we still recover the right behavior of deterministic chaos now that we have imposed these slightly different optimization techniques, where basically is our right-hand side still behaving in a physical manner? And the answer is no, we did not lose it. We still retain it. So over here, I'm basically perturbing my initial condition with a certain amount of noise, and I'm seeing how this is basically the difference between the ground truth and the perturbed system for a regular neural ODE and the multi-point neural ODE, which is the case with the new optimization technique, and also the spectral code, which is noise added to a solver. And you can see they are basically diverging at the right rate. When we reduce the noise, the divergence also happens later, again matching how it does in the spectral solver, and so on, right? When we reduce the noise even further, right? So this is something that is promising, because you know, a lot of these methods ultimately we want to use them for realistic applications where we want to generate ensembles, for example. And I have one at the moment. So you know, let's say that we go to at least the most challenging, one of the most challenging benchmarks out there for learning dynamical systems, which comes from the ERA 5 dataset. Over here, I'm not a climate scientist. I have no idea about the equations, and even atmospheric scientists debate these. I don't have ideas about the equations for the temperature, the specific humidity, the zonal min, the minimum. So these are variables that I'm trying to model, both in the short term and the long term. But there's a benchmark out there which is available for 40 years. We use a smaller amount of data just for the purpose of for demonstrating the prowess of our proposed work. And so what we have over here is, you know, exactly the same idea, except that over here we deploy this on a UNet type of architecture rather than a fully connected neural network on the right hand side. So our model is able to learn a short-term prediction. Again, I will have qualitative assessments in a bit. But short term is really not what is interesting. In the short term, there are many methods out there, such as the work out of NVIDIA, Google, and so on and so forth, that have killed this problem effectively. There's not much to gain over there. But what we're interested in is basically how we do in the long, right? So for example, if I plot what the short-term result is, typically we get an improvement on the regular neural ODE in the sense of the ensemble, by prescribing this newer type of optimization formulation. Remember, I don't know what the equations are, so I can't impose them. And so, as you can see, towards the 200th time step, these are 6-hour time steps for the atmosphere. So this is pretty short term for the planetary weather. You're getting a higher error in the mean squared error in the neural ODE compared to the multi-point neural ODE. But what we're concerned about is basically, can we capture the annual variability for something that's trained on a rollout for a few days? Can we then roll this out for years, right? So over here, I have a forecast for 3 years where I'm plotting the annual average temperature, wind speeds, humidity, and so on. and the black line is coming from our training data. Essentially, that's our test data rather from the ERA 5 data set. The blue line is what comes from this improved optimization, and the orange line is what comes if you use a vanilla optimization formulation. So over here, as you can see, even though you're stable, you do not capture the right amplitude and the frequency for many of these important variables, right? So this is an example of how changing the optimization and making it chaos aware, or aware of the fact that there is a the mean squared error is effectively like kind of like a flawed metric, actually helps performance quite nicely. Finally, we just wanted to also apply it to another challenging benchmark, which is not global but local. But there's a lot of work out there that has been done for forecasting the atmosphere, but we wanted to look at the ocean, which is actually also very important to the atmosphere. So that's probably the next step in a lot of SciML model development. So this is a region in the Gulf of Mexico where you have these eddy events, which eddies of the ocean. So localized regions of higher velocities or heights come in. These actually influence the formation of hurricanes in the Gulf of Mexico quite significantly. And we wanted to predict the evolution of these systems in the long run. These are very, very short time scale, long time scale problems. So you need to kind of roll out for long terms into the future. Over here,
Romit,
yes.
is data available freely for this?
We have to pre-process it. The raw data is available. Yes.
Okay.
Yeah. Yeah, I'm happy to share. I can share this with you. So as you can see over here, I mean, it's the same story, right? I mean, if you just use a standard neural ODE with the right-hand side given by unit, you have short-term predictive power, but in the long run, you get non-physical eddy structures, as against when we have the multipoint. This is very recent work. I mean, we're just starting this type of work. So we do, for example, not compute some gradients accurately over here in comparison to the truth. So there's still some work to be done. We're not sure about how to impose boundary conditions in this problem either, because it's a regional type of approach. So some open questions that are keeping us interested. It's just a video of the same thing, right? When you have like a standard neural ODE, you see these unphysical sort of striations show up. We stay physical, but then we don't capture this sort of dipole behavior in our model. So still some work to be done. In terms of raw metrics, again, it tells us that the application of this multi-point optimization within our neural ODE, we end up getting a slightly lower RMSE as we go into the 4-month range compared to the standard unit, right, in the ensemble sense. The dashed line is persistence, which is, if you're not familiar with persistence, basically that's a no-brainer prediction where the prediction, for example, 40 days from now is basically the state of the dynamical system today. So you can think of this as a free forecast for the future, right? So you say that the weather tomorrow is the weather today, or the weather 1 year later is the weather today, and see how you do against that. You should at least beat that, which both these data methods do. Okay, so I think this is the right time to conclude. So I want to conclude with some open questions, right? So there are still some open questions about, generally speaking, machine learning for dynamical systems, but also the work that I discussed. We're interested in learning what is the right quantity of interest for a system, right? So what is the right quantity of interest for the system, and how much of that quantity of interest do you need? A lot of these examples, we've kind of matched trajectories. These trajectories have either come from sparse sampling of a high fidelity data set or the high fidelity data set itself. And so frequently these are not available, right? So you have an added complexity of insufficiently observable data. The ocean is a good example of this. You can see the surface of the ocean, but you can't see what's happening deep under it, right? So in such cases, it doesn't matter what your optimization technique is. Perhaps you're never going to do well, right? But in such cases, it might be better to have equations imposed with your best guesses, really, and then back out a correction to those types of problems. But it's impossible to know ahead of time if the quantity of interest you're observing is enough. So that's something that that keeps us up. Other thing is, we've demonstrated empirically the fact that these tricks we are using actually lead to stability, but we are not guaranteeing this. There's some work out there, both empirical and theoretical, which says that there are some upper bounds based on the Jacobian of the neural network of the right-hand side. So the Jacobian kind of controls the growth of error in the a posteriori sense. We have some work on this, but there's still some open questions over there. And finally, we are of course interested in multifidelity data, which means that you have snapshot data from ground truth, but frequently these data sets themselves may be having varying resolutions in space, and in addition to varying resolutions in time. So there should be some acknowledgement of that fact in any work that we're building. So these are some things that we are studying at the moment, and yeah, I'm excited to talk to all of you for possible collaborations and questions. So yeah, I'll stop now, Maya, and let you ask questions.
Thank you, Romit, for a wonderful and very informative session. So I'd like to open the platform for questions from the rest of the people or the participants in today's talk. So please feel free to just unmute and even show yourself over the video to maybe ask a question. So yeah.
Yeah, I also want to very briefly give credit to my students who really pushed all this work. So yeah, and I'll leave this slide up here. Yeah.
So maybe if I could ask, I think I had just two questions that I had from my end
Sure.
Throughout the presentation after I got to see everything. So maybe the first thing is something that you discussed almost towards the mid of the presentation, which is dealing with the closure modeling of LES equations. So I was just wondering about how. So basically, I believe you must be using fine-scaled data from DNS to train these models to perform the closure modeling in the subgrid. I hope I'm right to say this.
Not necessarily. Not necessarily. We don't use fine scale data. So the idea is this, right? I mean, we basically have a formulation where we back out, we interpret closure as an inverse problem, basically. So we back out a correction term, but the ground truth can come from sparse samples of the ground truth. So basically, we don't need DNS essentially.
Okay.
Right? So even in this case,
okay.
We don't assume any filter. We just assume that we have some random samples, for example, of the fine scale solution, right?
Okay, random samples of the fine scale, and you're just extrapolating it to a coarse grade, like 64 square, as opposed to 250. So my question here was if you're moving from a very fine grid to a coarse and a grid.
Yes.
What I expect, it's not exactly averaging, but you can say that it's kind of a few of the flow features might be maybe averaged out due to the coarseness of the grid. So I was just curious to know, when you're having a data from sort of 256 grid size. When you're extending it to a smaller or a coarsened grid, do you think the error, do you think applying that model to this coarse grid would propagate some error for the model not accounting for this coarseness?
Certainly, yes, certainly there will be an error. But our hope is, I mean, firstly, you have when you say there will be error, there is going to be error in the sense of not capturing the fine scale. So that error is irreducible. You can't do anything about that, right?
Yes.
I mean, but what we do in LES is typically we try to model the effect of the fine scales on the coarse scales and hope that the coarse scale correlation remains, which is kind of what I'm showing over here, right? So what I have over here is samples. I mean, it's uniform sampling, but you can also do random sampling. It's easier to plot uniform sampling. Uniform sampling from the 256 square grid on the 64 square grid. And so obviously, the best I can do is match what I have on the left over here, right?
Right.
Because
Okay.
the
Makes sense.
fine scales are not going to show up, right? Because
Yes.
this
Yes.
is just not enough support for them. Yeah.
Yes. And second question is like connected to the first one. So when you're thinking about sparse sampling,
Mm-hmm.
when you look at applications such as compressed sensing, I believe sparsity, you take sparse samples from measurements and then you try to reconstruct the original signal. So there
Yes.
always this question of optimal sampling always arises, because the moment you
Yes.
are out of this optimal sampling threshold,
Mm-hmm.
then whatever you get out of that is going to be junk. So you don't have
Yes.
to have, like, there is no use of this reconstructed signal.
Correct.
So is that something that is also accounted for in such kind of studies, or
No,
is it?
no, it's not. So it's a good question. It basically means that we have to wrap an optimal experimental design loop around this,
Okay.
which is certainly of interest to us and probably a good thing to address in the next step. But if you sample in a non-informative area, yeah, there is no hope for you to learn anything, right? So this is all
Sure.
under the assumption that you've sampled adequately, right?
So the takeaway is that depending on the problem, we'll have to perform. It's more like a tuning this parameter and arriving at the best value for the threshold for sampling. It's like,
yes. The
yeah.
number of points and the location of points is always going to play a critical role.
Okay.
And if you want to optimize that, then you have to take some of these methods and wrap them into an outer loop for OED, right? And yeah, that adds its own overhead. You're right, absolutely right. And but for example, the work that I mean, usually the advantage we have as knowing a little bit about the physics is that um, we can kind of know where to sample. So for example, if I have a separated flow and I want to back out a closure for this system, what we do in our work is we don't sample upstream, right? I mean, because it's common sense that we don't want to sample upstream. So there is usually some understanding of the flow that helps you sample at the right locations. Over here, what I'm showing you is the model is actually spiking near the shed-in areas
Yep.
because it's learned a closure. But then the sampling I did for this particular problem was all downstream of the step after 0.2. So even though I looked at only this region, it's able to correct in the region upstream, right? Because it learned some of the physics. So yeah, it really you have to rely on your understanding of the problem
Yes.
to sample accurately.
Thank you for that. So I
Yeah.
think that's pretty much all I had for at this point. So, but again, thank you for a wonderful informative session. So maybe
Sure.
I'd like to again ask other people, in case if you have any questions, please feel free to ask at this point. So otherwise, I'd.
Romit, just one thing.
Yes.
It's not question, it's request. So basically, the ocean model data which you are using, uh, is it I mean, is it high fidelity or low fidelity data?
It depends on who you ask. So I mean, I think for the
You said that you are basically pre-processing it, right? From the raw data.
yes.
Okay.
Yeah, it's three variables: sea surface height, sea surface velocities, UNV, and it has a uh, um, I forget the temporal resolution, but basically it depends on what you want, right? You can have a very fine temporal resolution. I think what we have is a resolution of a day, but you can get it at hourly timescales, and I think the dimensions are somewhere around I want to say 400 by 500, something like that. So so it's not super large, and yeah.
Yeah.
Mm.
And so maybe I'll contact you later regarding that.
Sure, sounds good. Yes.
So thanks, Romesh, for coming and giving such a wonderful talk.
Oh, absolutely. And thank you for the invitation. I don't know if there were any other questions, but if not, feel free to email me. Happy to go into a lot more detail if needed. Right. So yeah.
Okay.
I'll stop sharing now.
Okay. So
Okay.
should I
Great.
I'll stop here?